theory. Now I don't really have like this super like I know exactly what I'm doing today. I feel like with you guys, the best thing to do would probably be like just kind of have conversations and be able to interact with you and talk with you and all of this kind of stuff. So let me start the new movie recording. Look at that. And then let me log into Canvas over here. Mr. Dalday. There we go. All right, 1 second. Give me a second. I'm working. I'm doing this. And then here. Conferences. Join. Okay. All right, I hope this is not too much for my simple computer to be able to handle. Check. There we go. I know. There's going to be some feedback, but I anticipated for that. Let's get started on this theory, shall we? So let me just do this, and then start the recording. All right. I just got logged out, so I'm able to use my mic. Awesome. Julia, I love when you talk to me. Julia, can you say something? Yeah, I can hear you perfect. Awesome. Let's start this part. Okay, there we go. And this goes right here. I start this recording. And I think we'll be good. There we go. All right, let me grab this and start the recording and do this. Awesome. Okay, here we go. Julia, can you do me a big favor? I can't actually see this chat screen. Actually, you know what? I can move it so that I can. Hold on 1 second. Okay, let's see. Conferencing. This right here. This right here. Options that. Make the size 16. There we go. Awesome. Cool. Okay. Let's do this. All right. This is kind of off the top of my head. We'll see where we go with this. We'll see how far I can do this. All right. What I've covered with you so far is work is equal to force times distance. And the idea behind this is the force is actually measured in newtons, and this is the units. The force is measured in newtons. The distance is measured in meters. So you have a newton times a meters. We named this after this dude named Joules. And so it's also known as a joules. That's what force times distance is. That's what work is measured in. Hey, where's my cloth living? Hold on 1 second. Where is my... oh, there it is. Got it. I see it. All right. So work equals force times distance. Joules is the same as newton meters. Another way to play with the units would be kilograms, meters per second squared times meters is the same as joules. Do you see how that newtons actually just changed over to kilogram meters per second squared? Do you guys see that? Yes, no? Because a newton is a force, and a force is equal to mass times acceleration. Kilograms is mass, and acceleration is meter per second squared. So it's also known as a kilogram meter squared per second squared. I'm just looking at just the units here. Am I freaking anybody out yet? No. Yes. Maybe. Are you guys chatting back with me? I can't tell. Oh, okay. Did you guys say something and I just can't see it? Try chatting back and say hello or something like that. Okay, there I can see you. All right, good. You guys just weren't talking to me. All right. I introduced to you this concept of, all right, let's go through some more equations. I introduced to you the concept of kinetic energy, which is 1/2 mv squared. Now, I denote that with a KE, and I say, all right, the kinetic energy is mass times velocity squared. Does that make sense? Oh, by the way, I'm sorry. This is joules, which is the same as kilogram meter squared per second squared. which is also the same as Newton meters. I can play with this thing all day, and that's how I would get it. This thing right here, kinetic energy is 1/2 mv squared. Where does this m come from? Well, the m comes from, I mean, imagine if you can think about it like, when I think of energy and work, I think of pain. So if I'm playing football and I've got somebody running at me full on, like running at me, like they're like, "Ah!" and they're like foaming at the mouth and whatever, then I would be more afraid of a 200-pound man versus a 100-pound man. Would you guys agree? Like, I would be more afraid to be hit by Dustin, the 6th grade teacher at the school, who's a rugby player, used to weigh 280 pounds, versus being tackled by Julia, who, sorry Julia, I know that you're tough, I'm just saying, you know, I'd rather not be tackled by the 280-pound rugby player. Would you agree? Yes, of course you agree. Spelled it, makes sense. Yeah, exactly, there we go. So mass has something to do with it. I also would be more afraid if Dustin were running with a high velocity than a low velocity. So that's why kinetic energy relates to this thing. It would cause more pain if the velocity increased. All right. Let's check the units to make sure that this equation actually is a valid one. This m over here is measured in kilograms. This v over here is measured in meters per second. But I square that sucker, and I end up getting meters squared per second squared. Oh, the 1/2 doesn't contribute any units to it whatsoever. So can you see how this expression right here is really an expression for energy, work equals force times distance? Are we cool? Awesome. There's another equation that I gave you. Let's do this one. Potential energy. I don't know if I've covered this with you yet, but let's talk about this one. The potential energy. What would you use to define the word potential? If I ask you, what does potential mean? How would you define it? The ability to do something, exactly. So maybe let's say potential energy in terms of our pain exercise is the ability to cause pain. So where's my weight that I had? I had a weight over here and I was dropping it on my head and it was really sore. Let's do this. Okay, hold on 1 second. Let's find something to drop on my head. Hold on, there we go. Not CE. 1 second. Okay, wait, I'll grab something else.
And just one page, value of the exchange is going to have a huge impact. Okay? So, here's the formula that I actually put these formulas on your lab document that you need to keep in mind. So, carbon dioxide.
Okay, all right, I got it. Okay, so check this out. Whew. All right. Potential energy, the ability to do something. If I have something that has a small mass, I put it over my head, okay, and I drop it. Ow. That kind of hurt. Actually, it hurt yesterday when I dropped a 2-kilogram mass, like a steel mass on my head, to show Julia. Actually, I think that was Wednesday, but that's not so bad. However, if I take this 25-pound weight and I put it over my head and I drop it, which would you be more afraid of? Which would have the ability to cause more pain? This thing or this thing? Come on, talk to me, interact with me. The heavier mass, exactly. So the amount of potential energy is dependent on the mass. And the reason why I say which one would cause more pain is because I want to know whether or not it's directly proportional or indirectly proportional. If it's directly proportional, then it goes in the numerator. If it's indirectly proportional, it goes in the denominator, or I make it 1 over, that number. What I mean by indirectly proportional is if maybe the weight increased but the pain decreased. You know what I mean? This obviously is directly, so it would go in the numerator. All right, now I got a question. Which scenario would you say has the ability to cause more pain? Here or here? Scenario 1 or scenario 2? I'm going to break this piece of glass in front of me. I'm just going to drop it and it's going to break it, shatter the glass, I bet you. Scenario 2, exactly. Scenario 2, what did I change? I didn't change the mass, but what I did was I changed the distance. Now, I don't want to say distance specifically because, all right, let's talk about distance, okay? If I have it here and I move it a distance, I move it a distance maybe this far, will it cause any more or less pain versus moving a distance? Does this make sense to you? What I mean by distance is I don't want to say distance, because distance just kind of implies like any kind of movement. No, not displacement. What I mean by it is my potential energy is dependent on a very specific type of distance. Is dependent on height. It's dependent on the vertical distance. Because moving it horizontally won't really change the amount of energy that I'm giving it, right? Right, exactly. Because moving it horizontal or moving it vertically changes where it's placed in the gravitational field. Something like that. What is the last thing that potential energy must be related to? The amount of pain that's that is induced. And you have it in the sentence that you wrote back to me, that word you have. What does that say? Gravity. Think about it like this. If I'm holding that weight above my head on Earth and I drop it, that would be sore. If I'm holding that weight above my head on the moon and I drop it, will that be as sore? And Julia, please talk back with me. Use your microphone. The other two girls, you can talk back. I'd love to hear your voice. Or what you'll probably have to do is just type back. If I had it on the moon, would it hurt as much? Will it have the ability to cause more pain? Greater gravity, greater potential energy. I like the way you said that. Exactly. If I'm talking about if I increase the amount of gravity, then I'm increasing the amount of pain that it could cause. On the moon, it has less gravity, so the pain that you would experience is less. Versus if you put it on Jupiter, which is 16 times the amount of gravity, that thing would kill you. I mean, I wouldn't necessarily say you'd be very safe when you do it on Earth. But, All right, Catherine, I think what you're trying to do is, how do you see the video and chat at the same time? I think you made the video full screen. Whereas, as opposed to making it like that really small screen. What you might want to do is take that screen, the really small screen, and drag it so that it's proportionally big. And then you can chat and see the video at the same time. All right, so potential energy is a measurement of gravity. Let's check the units on that. Gravity is measured in meters per second squared. Mass is measured in kilograms, and height is measured in meters. So the units for potential energy is meters squared per second squared times kilograms. Hey, wait a second, that's still joules. So we're in the clear here. Do you see how all of this? Do you see how all of these equations are? I mean, these equations have the same units.
So what we're going to do is we're going to actually
Alright. Okay, so here's what I'm going to do. I'm going to do one more because I feel like this one's a little bit more obscure, and I don't know why I taught this to you earlier. I actually just was following the book, but then I'm looking at this, and I thought to myself, I'd rather just kind of like talk to you about the whole thing as opposed to just follow the book. So here's me talking to you about the whole thing. Let's take a look at this one. A spring has a force related to it. That force is K times X. I taught this to Julia and I recorded some videos, so I'm not going to go too deep into this, but I will tell you what the measurement of K is. K is measured in newtons divided by meters. Are we cool with that? Okay. Because X is measured in meters. So if K is measured in newtons per meters, then when you multiply this times a meters, you end up getting newtons, which is what a force is supposed to be measured in anyway. All right, let's keep that in mind. What I can talk about now is I can also talk about the amount of potential energy in a spring. What I do sometimes when I teach physics is I hold a bow and arrow up in class, but I didn't bring my bow and arrow today because I couldn't carry it on the bus. I'm serious, this is what I do. I pull back the arrow, the bow and arrow, and I point it at someone's face. Hint, hint, it's not loaded. But people get really scared. And I say, how much energy, or how much potential energy does this thing have? Because it has potential energy. It's not hurting you yet, but it can hurt you. Right? So it is a form of potential energy. It just happens to be energy that's stored in some kind of rubbery thing, like the bows of a bow and arrow, or the rubber band, or a spring, or some kind of elastic thing. Am I making sense here? So this is a different form of potential energy. Sometimes what I like to do is I like to call it potential energy with a little s on the bottom of it, as opposed to potential energy as attributed from gravity, which I like to call PE with a little g on the bottom. Are we cool? Have I lost anybody here? Now the potential energy in a spring, I'll give you the equation for it. It's 1/2 kx squared. Let's check this to make sure that it's got the right units for it. The k is measured in newtons per meter. The x squared is measured in meters squared. One of these meters on the bottom cancels out with one of those on the top, and you end up getting newton meters, which is the same as 8 joules. We're good with this equation. Okay? But this is the spring energy that you get. Now, when do you use this? How do you use this? Well, I'll show you an example problems. But these are pretty much the 3 forms of mechanical energy that I can tell you about. This is all of the stuff that we need to cover. And I believe that I only introduced to you maybe these 2 in the first chapter and then this one in the second chapter. And I think that that was a mistake. I should have just kind of introduced to you the whole concept as a whole altogether. Now, let's talk about how we want to use this stuff and maybe how to apply these equations. And then what I'll do is I'll do some really fun things where I'm going to have like an iron close to my face, and then we're going to drop it and make it swing and all of that kind of stuff. It's going to be a lot of fun. I'm going to erase this. So I've given you 4 equations to work with here. Work equals force times distance. Kinetic energy is 1/2 mv squared. Potential energy is mgh. And spring potential energy is 1/2 kx squared. How would I use this on a pendulum? Here's the really awesome thing about energy. I froze. Am I still there? Julia, can you not hear me? Oh, shoot. Okay. Julia, 1 second. Let's stop that. Okay, sorry, 1 second. 1 second. Check, check, 1 2, 1 2 1 2. Hello? Yes, I'm still here. I'm sorry I froze. The computer that I was using for the video camera got screwed up. Give me a second. There we go. Oh, that's not what I want. Okay, here we go. All right. Still can't see. I know. I'm working on it right now. I'm giving you eyes right now. Is the audio coming through? You getting good audio? All right. And the video you can see? Okay. So let's do this. Here's some of the things that I think are really nice, and I think that are going to be really cool, and I'm actually really excited about it. Give me a second. Something's wrong with my video camera. Okay, let's see. Let's close this. Oh, perfect. All right. Here's something that's really cool, and I think that's really exciting. I think that you'll be excited about it too. Why do we use energy, and what is the advantage of using it? You can use energy to replace some of those kinematics equations that I showed you. You'll actually find that it's easier to do things using energy and looking at the world through energy if you don't have to deal with a pesky thing like time. Let's try a pretty basic problem. Let's talk about dropping a ball from a height h. And I want to figure out what the velocity is going over here. Okay? Here's what I can do. I can take a look at how high this thing is, and I'm going to use old school kinematics equations. I'm going to do it pretty quickly, so try to keep up. I would say that the equation I would want to use is delta x equals v naught t plus 1/2 at squared. You guys remember and know and love this equation. My velocity initial is 0. My acceleration is g, and my delta x is h. So h is equal to 1/2 g t squared. So my actually, I'm sorry, that's not the equation I want to use. Is that the equation I want to use? All right, fine. Yeah. All right, I'll use that equation. So my my time that it takes is 2h equals gt squared. So t is equal to 2h over g with the square root of it. But that's not what I was asked to solve for. I was asked to figure out what the velocity is. So now that I have my time that it takes to hit the ground, I can solve the velocity by plugging it into v equals v naught plus at, v naught was 0. So I just basically multiply this by g, and I end up getting v equals g times the square root of 2h over g. I can make this the square root of g squared, the square root of 2h over g. And then I can make this v equals the square root of 2gh. Are we cool with that? This is old school. This is like, hey, remember this that we did? All right, good. Why don't I write that answer down over here? V equals the square root of 2gh. Okay? Now I'm going to approach this problem with using energy and talking about energy. What type of energy does the ball have when it's up here? What type of energy? There's three. There's potential energy. Now you have to be specific, and I know it's kind of obvious here, but is this gravitational potential energy or spring potential energy? Yeah, exactly. You need, yeah, PEG. It's the gravitational potential energy. So what I'm going to introduce to you is this concept of energy is conserved. All of the energy you have in is equal to all of the energy that comes out of the system. So what kind of energy is at the beginning of the system? That's potential energy. Is there any kinetic energy in the beginning? No. So It's not moving.
Okay,
There.
here is, I'm gonna give
And that's going to equal to all of my potential energy in the end plus all the kinetic energy. How much potential energy does it have at h equals 0 over here?
before and after. Okay?
Well, if the equation for potential energy is mgh and h equals 0, then it has no potential energy.
The other is for
Right?
acidic water. Or processing.
So where did all that energy come from? Well, it came from, or where did all that energy go? It went into moving the ball, so it has kinetic energy down here. I'm looking at two different pictures. At the beginning, it has potential energy. At the end, it has kinetic energy. Potential energy is mgh. Kinetic energy is 1/2 mv squared. I want to solve for v, figure out what that is. M cancels with m. Multiply this up by 2, so 2gh equals v squared. Square root both sides. Square root of 2gh equals v. You want to see something cool?
If you are curious about the pH of your vinegar solution,
That's the same equation.
make sure that you use as well.
You can look at these kinds of problems with the energy glasses on as opposed to the kinematics glasses on. The disadvantage is when you look at things with energy, there is no time in this equation. So if I ask you to find how long does it take, then you'll have to be forced to go back to those old school kinematics equations. But if I'm asking you like how fast is it going, then you can use these things. Now, here's the thing that makes it really cool. I'm going to kind of tie it all together here. You can actually do problems using energy that you can't do using kinematics. For example, and this is where it becomes relevant. Say I have a pendulum, all right? You know what a pendulum is. You put it up here, it swings back and forth. My question to you is, how do I figure out how fast it's moving right here? I know the length of my pendulum is L, and I know the angle that I moved it at is at theta. How do I figure out how fast it's moving right here? Okay, what you do is this. I set up my energy equations. I do the conservation of energy. Maybe the easiest way to write that would be PE plus KE equals PE plus KE. And I put a little I here, F here, and an F here. That stands for the potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. It's saying all the energy added up in the beginning is equal to all the energy added up in the end. And if I had a spring in here somewhere, I would throw in the potential energy with a little s on the bottom of it. Does that make sense? So I'm adding up all the energy in the beginning and adding up all the energy in the end. My question to you is, how much energy do I have in the beginning? What kind of energy do I have at this point right here? I have potential energy. Do I have kinetic energy? So what I do is I put a little 0 right here. I just cross it out, put a little 0. In the end, do I have potential energy? When the ball's down here? No. Right. I don't have any potential energy, but I have kinetic energy. So I have this equation mgh is equal to 1/2 mv squared. The masses cancel. That's interesting. I move this 2 up here. Take the square root of both sides. So I have v equals the square root of 2gh. Here's the hard part. Here's the little trick, but it's really a little trick, is I don't have the height at which I dropped it. How high above this point did I drop it at? What is the vertical distance between the initial point and the final point? But you can find that using basic trigonometry. I mean, I could ask you this question on the SAT. You would know that the distance between here and here is L, right? From here to here is the length L. You know that the distance from here to here, if you look at this triangle, is L cosine theta. Do you agree? So the height that I'm looking for is this distance from here to here. It's the whole length L minus L cosine theta. So instead of writing an h, I'm going to have v is equal to the square root of 2g times L minus L cosine theta. That's the trick with the pendulums, but the pendulums are pretty simple and straightforward. What are your thoughts, comments, questions, etc.? All right, cool. Why don't we do this now? I'll be right back. I gotta go find a volunteer to help me out. Oh, perfect. No, actually, I gotta open the door. I'm just gonna swing it. All right. Can you guys hear my voice? Okay, so check this out. Can I get your help? Okay, so here's what I'm going to do. Let me see if you guys can see this. What I'm going to do is, we've been talking about potential energy, we've been talking about kinetic energy. I have an iron that I'm going to hold to my chin right here. And as I showed you before, it's attached to the door. Now let me ask you this. When the iron is at my nose, what kind of energy does it have? Exactly, it has potential energy. Then let's talk about how it's going to move. As this thing swings down, okay, it's going to swing down to the bottom of this thing right here. What kind of energy does it have down there? Think of it as moving. In your head, think of this thing as swinging through. Very good. It's kinetic energy. Where did that kinetic energy come from? It came from the potential energy that was up at my nose. Exactly. Then what it's going to do is it's going to swing on through, and it's going to go till it reaches the end over here. It has potential energy again, and that comes from the So then what it's going to do is it's going to come back, swing over here, and whack me in the face. Right? Let's see if that happens. Okay. I'm going to put this right here at my nose. I'm going to let it go. It's going to swing across. It's a very scary thing to see it on this side. Maybe I'll move the camera so that you guys can see it. But I'll show it to you at this angle right now so you can see how close it gets. Ready? Go. And it missed me. Thank goodness. Why did it miss me? What happened there? Because it loses energy. Exactly. When I told you that it has... Oh, I'm sorry. Let's close the door because I get excited and I don't want to talk too loud. Deceleration air resistance. Exactly. When I told you that the potential energy... When I told you that the potential energy in the beginning is equal to the kinetic energy, is equal to the potential energy, and then back to the kinetic energy and potential energy, and it doesn't get, it's conserved. It's not that I lied. It's that I didn't give you all of the pieces to the puzzle. Because energy is work, right? Work is force times distance. And like you're saying, Julia, there's air resistance. Because there's air resistance, that's work being done on the system. There's friction inside of that pulley up there. There's friction inside of the cord where it's touching, so it's rubbing a little bit. As it moves through the air, the iron is actually hitting molecules, running into air molecules, and you're thinking that's not going to cause much of a difference, but that actually does. It actually does technically heat up, and I don't even have it plugged in. That's energy that we didn't account for. So in a perfect system, that iron would come back and touch my nose again. It wouldn't go up any higher because I didn't give it any extra energy. I'll be honest with you, one time I actually did chip my tooth because I had a bowling ball up to my nose and I accidentally gave it a little push when I gave it some energy. So, and then it hit me in the face and it was really funny and I didn't think it was funny, but my class did and they really learned a lesson. This time I didn't push it and I made sure that there was some energy loss so it wouldn't come back and hit me in the face. Right. It's hard to consider all the variables sometimes. Yes, exactly. Exactly. So in physics, I'm doing an ideal system for you. We're doing this right here. I'm doing an ideal system. I didn't include any of the force, the frictional force that's in there. This is an idealized system. But what's nice about it is that, here, when the students say, what's nice about it is that I can teach you the physics of an idealized system, and then later on, if you decide to become an engineer or something like that, then we'll start teaching you guys how to apply the real world, small little, minute, as you said it, extra variables, Julia. What's your thoughts on that? Does that make sense to you? Because there's one more thing that I want to show you that I think is absolutely cool. I know that this might be even more nerdier. So that's my fun thing where I swing an iron back and forth. And I'll do it a couple more times if you want, because I know the students really get a kick out of it. But I did want to take the chance to show you this. So now I'm going to switch technologies, and this is actually something new for me, but let's see what we can do. I'm going to turn off the video camera, but I'll still have the audio going. Can you guys still hear me? Go grab a chair right outside. Okay, all right. Good. So let's do this. I have you on Firefox.
Are not responding to.
They have trouble hearing sometimes, but yeah, I'm not sure. Kiko and Catherine, can you guys still hear me? All right. I'm going to actually log out and log back in real quick because I want to make it so that I'm the manager of the system. Yes, I know. I told you I would turn off the video. I'm going to log out and log back in. Hang out there for just a minute. Log out, log back in. Come back in as the teacher on this computer because I want to show them my video screen. And Firefox doesn't work with this one, and yeah, there's all these variables to consider. Okay. All right, here we go. Microphone, yes, I want this. Share select device. Okay, yes. Good. Audio. Audio coming through, yes or no? Good. Kiko, Catherine? All right. So, I'm not going to share with you my video because what I want to do is I want to share with you my computer screen. I'm going to switch over to some ideas with you on this one. I'm using this program called Tracker, and I think this Tracker is pretty cool. I'm going to show it to you and how it works. Give it a second because it takes a few seconds for it to share the computer screen here later. Then it should pop up here, and there's another thing here. Okay, there we go. Perfect. Awesome. Tell me when you guys can see my computer screen. I'll remind me later. Come on. There we go. Run. Should pop up now or soon. There we go. Awesome. Can you guys see the computer screen? Hello? All right, good. So, what do I want to do with you? All right, here's what I got. What I did was I took a video of a pendulum, and this is just a straight up pendulum. It's a very simple one. See, this is just like the iron. There's a little thing where it's connected to, there's a string, and I have a mass on there. Now what I also did was I put a green piece of tape on the end of this 2 kilogram mass. So that way I can see it very clearly. And I'm going to send you this data, and this is what your homework is going to be. You're going to be processing this information, this data. What's nice about this is I actually use this program called Tracker. It's a free video analysis program that you can download. However, you cannot use it on your Chromebooks. So there's that. But let me show you what I did is I tracked the XY coordinates of those points right there. And so what it's doing is it's picking up, it's finding that green dot all over the screen. Now what I want to show you is some nice things about it. Let's see. Okay, let's do this. Check this out because I think it's really crazy. Do you see this graph right here? This is the X. Do you see that graph? Yes or no? All right. This is the X coordinate as plotted as a function of time. But here's what's really cool about it. Okay? is this right here is a sine wave. Do you guys remember from trigonometry, or some of you are in trigonometry? What really excites me about this particular graph right here, and I know you guys are thinking, well, it just goes up and down like that. Yes, but when I teach trigonometry, I always get the question, why should I care? Why do I have to learn sine waves? That doesn't make any sense. And my answer to it is this. Look, it appeared in nature. I just took a video of a thing swinging back and forth, and I get a sine wave. I get something from one of your that you feel like, yeah, exactly. Trigonometry graphs don't seem applicable, but they totally are. That is why we teach you the trigonometry, so that you can do stuff like this. So what I do is when I teach trigonometry, I have to tell them, well, if you were to graph the position versus time graph of a swinging pendulum, then it would give you the sine wave. And they'd be like, yeah, whatever. But this is where it comes into play. This is why we're teaching you to in the first place. That excites me. But let's take a look at this, okay? I'm going to look at the velocity of this thing. And I'm going to look at the height. All right? So all I did was I graphed this thing, and I have the computer show me what is the velocity of this graph. And at the same time, I want to see what the height looks like. All right. Before I forget, let me tell you, I can look at it as a table, and this is really just the same thing. This is the plotted version of this table. I'll send you. Actually, I made a Google Doc of all of this data that I will send over to you, and so you're going to be able to analyze the exact same thing this computer program is doing. But I want to tell you this. Let me ask you this. Look at the height. Look at the velocity graph. Where is it at its highest velocity? Tell me what the value, the time, at what time is one of my highest velocities? You got to look at the graph. I'm waiting on it. 0.5, exactly. All right. Now, look at the height graph. At 0.5, what can you tell me about the height of this thing?
If you guys want to log into the smart view that's on your phone,
The highest velocity when the height is 0. Exactly. My height, if you see how I set up my coordinate system, I put my coordinate system at the lowest point at which this thing goes to. When this thing goes to a height of 0, it has its highest velocity. What is that telling us? Think of it in terms of the potential energy and the kinetic energy. Why does it have its highest velocity at its lowest point? Where did it get all of that high velocity from? All right, no, I want you to process this. I want you, all the graph. It's yes. Yeah, actually, that's exactly it. It got all of that high velocity from the potential energy, and since all of the potential energy is gone down here when it's at its lowest point, it's going to have its highest velocity because that potential energy turned into kinetic energy. Do you see how these graphs work? Yes, exactly. It transferred over from potential energy to kinetic energy. All right. Now, I want to show you something that I think is really cool. I hope that you feel like that's cool. I hope you feel like, that's really interesting. I didn't know that. What are your thoughts? So I'm not doing magic here. I'm not showing you something crazy. All I'm doing is I'm showing you I'm just showing you a simple pendulum. I mean, you can make this pendulum at home. You just take a string and tie it to something and have it swing back and forth. You have a pendulum inside of the grandfather clock that you might have at home. Yes, I love how it all fits together. It makes me excited about that. Yes, AP Calc and AP Physics go hand in hand. Now, let's take a look at this thing right here. All right? Because I think this last graph is kind of interesting. This one might actually be easier for us to understand. I was actually probably supposed to show you this before I showed you the, I was probably supposed to show you this before I showed you the, why can't I think of it? Oh yeah, the pendulum. It's a simple ball rolling down a slope. Remember solving these? They're called inclined plane problems. It's where you shift that coordinate system down sideways. Do you remember doing these problems? Yeah. All right, cool. So, what it's doing is it's basically just rolling down the hill and it's slowly speeding up. I think what's really interesting here, and I'll send you the data for this plot as well, but I feel like what's really interesting to me here is when you look at the height plot right here versus the velocity plot. Obviously, as the height is decreasing, the velocity is increasing. Do you agree? Come on, Kiko and Catherine. If you can jump in, that would be great. As the height is decreasing, you can see the velocity slowly increase. But here's the thing that really trips me out. The thing that I thought was interesting. Look at, or what kind of graph would you say this is? Is it a linear graph? Is it quadratic? Is it cubic? It's a scatter plot, yes, but I mean, what curve best fits this? It's a linear association. That's what, I agree. It's linear, okay? Now look at the height. As the height decreases, what would you say? Is this a linear line? It's exponential. No, it's not necessarily exponential. Exponential would grow a little quicker than that. It's actually parabolic. But do you see how this one is a parabola and one is a line, and when we relate the energies, one is linear in a function, whereas the other one is parabolic in function, which is kind of hinting to us as to why we're having this velocity squared is related to just the height. Does that make sense? You can see from the graphs why I have one being a velocity squared, whereas the other one being just regular h. Now, Kiko, I apologize. I know that you're supposed to actually be tutoring. I don't even know if you're listening because you're probably going after the tutoring session. And hey, man, that's cool. I appreciate that you came and you hung out this long. But what are your thoughts? Like, does this put it all together? Does this blow your mind? What's up? So I feel like I've redeemed myself, and I've done a good job at going through all of the theory of everything I need to cover with you. Okay. But what I want to make sure to do is after I go through all of the theory, I want to make sure to do some example problems with you. And so next week, Wednesday and Friday, I'll cover up some example problems with you. Are we cool? All right. Awesome. Kiko, I want to thank you personally for hanging out. Julia and Catherine, thank you so much for coming. You've made this a dynamic class. I actually am really excited. Do you care about seeing the iron swing and try to hit me in the face again, or are you guys good? Do you guys want me to move the camera and try to hit the camera in the face? That way you can see what it looks like? All right. Sounds like that's not as impressive to you guys anymore. I'm fine with that. All right. I'll talk to you guys later. It was great to hang out with you today. Thank you so much for your time.